Yesterday we had some nice talks from Mark and from Peter talking about how the climate is changing and how it changed in the past, and talking about sensitivity of the climate to things like atmospheric CO2. And then we had a talk by Georgina where she was telling us about biodiversity and about how global biodiversity has changed over time and why it's important to conserve biodiversity. So what I want to do today is to make the link more specifically between climate and biodiversity, thinking about the responses of biodiversity to climate, thinking more specifically about shifts in species distribution and how they respond to climate change, and then go on to think about specific conservation that we might choose to carry out to help species respond and adapt to climate change. So we've seen lots of these graphs already showing how the temperature has changed globally and how it's getting warmer. And the plot that I've chosen to show illustrates the fact that since the millennium, most of the years since then have been in the top 10 for the years with the warmest years on record. And this also gives me an opportunity to explain that I'm going to be focusing specifically on things in the UK in terms of some of the empirical data to show how species have shifted their ranges. But I'm also going to be giving you some examples of some other work that we've been doing down here in Borneo, and hopefully you will see that these two things do fit quite nicely together, or they're from quite disparate locations. And I've also included a picture here of a speckled wood butterfly. So one of the taxonomic groups that we work on a lot, but not exclusively, are butterflies, and they're good for many reasons for understanding and mapping responses of species to climate change, not just because British people really like butterflies and spend a lot of their time recording them, and they're absolutely fantastic records going back over time, but because they're insects and they're poikilothermic, they respond quite rapidly to climate change impacts. And certainly in the UK, we've got a lot of species who reach a range limit to their distribution, which means very easily we can go out and look and study and see how the ranges are changing. And certainly here in York, we're really well placed because many species reach the northern edge of the distribution here, many of the southerly distributed species. So you get a lot of species moving through Yorkshire and heading north. And certainly in the time that I've been in York, which is getting on for nearly 12 years now. This is a butterfly that didn't occur in York when I first arrived in 2001, and now it's very common here, and it's motored north and it's moving up through County Durham and into Northumberland. So this is quite a good study organism to work on because it is responding to climate change and shifting northwards. And many of our butterflies are responding to the climate and to the climate change and to the warming. But if you read the most recent reports coming out from people like Butterfly Conservation and so forth, obviously a lot of our butterflies are in problems because of the poor summers that we have had. But nonetheless, they are a good group to work on. And we know, particularly when you start to look at the butterfly like the speckled wood, you find out if you go back and to look at some of the historical records, so some of these great records that have been collected over the last 150 years or so, you see that actually a shifting and a dynamic distribution is what the norm is. This idea that distributions are static is not the case when you start to look at these historical distributions. So certainly for the speckled wood here, its distribution has been heading north and retracting southwards over the last 150 years or so as the temperature has warmed or cooled. And here, this is the sort of type of responses that we might expect species to show as the climate changes. And this is sort of taken from the fossil record and the subfossil record. Essentially, species have got three choices. One is to shift their ranges and track climate, and that's what we see from fossil record, and that's what I'll be showing some empirical data for that. There's also the possibility, of course, for genetic adaptation and species to sit tight and try and cope with the changes. I'm not going to be talking about that in my talk today, although that's something that we have been looking at. And of course, there's the alternative about going extinct. And of course, depending on where you are and the location of the distribution, shifting their ranges will probably mean that at some point in their previous range that they will go extinct there. So I guess 1 and 3 here are linked in that way. So this is a meta-analysis that I-Ching Chen, a PhD student, carried out. And this is to show you the sort of empirical data that we can get to see how species are responding to climate change. So these two plots here have some quite nice characteristics to pick out the sort of patterns that we're seeing. So the one on the left here is showing latitudinal shifts. So these are generally species in the northern hemisphere heading northwards, but not only, they're the ones in the southern hemisphere heading towards the South Pole as well. And on the right-hand one here, we also have elevational shifts. So these are species that are shifting uphill rather than heading polewards. And the first exciting thing that I-Ching found was that based on previous meta-analyses, her analyses show that actually from her analysis they're about 2 to 3 times faster, these shifts, than had previously been reported. And what we have here is data points, and for each of these data points it's a particular taxonomic group at a particular location. And as you can see here, she's got quite a range of different groups that she was able to extract from the literature. And essentially, if this is a hollow symbol, it's a vertebrate, and if it's a filled symbol, it's an invertebrate. And what we have here on the y-axis in both of the plots is the observed shift. And what we have here on the x-axis is how you would have expected those species to have shifted at that particular site for that change in climate that occurred there, for the change in temperature. So this is based on things like lapse rates and working out how much the climate has changed and how much a species should shift. And then what she's put on here to help you is the one-to-one relationship. So if everything is moving and shifting as you would expect for the temperature change at that particular location, then all of these data points for all of these taxonomic groups should fall on this line. So you can see that there's quite a lot of variation, but this is a significant relationship here, so you get greater range shift where you get greater warming. So there's quite a nice mechanistic link coming through from this meta-analysis. The other thing to notice here is that within a particular taxonomic group at a site, there is a huge range of variability. So species are doing very different things at one particular site, even when you take account of how much warming there's been at the particular site. Interestingly here, there don't seem to be any lags between the shift and the expected shift. So you get an approximately equal number of data points above and below this one-to-one line. I'll show you an example in a moment where there are latitudinal lags. But we are seeing evidence here of elevation shifts upwards where there seem to be lags. And so you have less shifts uphill than you would expect for the degree of warming at a particular location. So if you move on now to a slightly older data set that Rachel Hickling, another PhD student, analysed. So now we're just looking at range expansion northwards across a wide range of groups here that are held by CEH. So basically she just analysed anything she could get her hands on. Don't worry about the different colours here. Basically for each of the histograms she analysed each taxonomic group slightly differently to try and get around the issues of recorder effort. But hopefully what you can see is, with the exception of these herptiles here, everything is heading northwards. So these are species heading north in the UK. Most of them significantly to a greater or lesser extent. But one of the things that came out of Rachel's paper and got us thinking very much about the role of habitat in terms of species response is actually what you can work out is how far should they have shifted for the level of warming that was observed in the UK over the time period that these data are from. And it's something about 120 kilometres north. So anything that's in this part of the graph above zero, this is heading northwards, and these are heading south. So all of these species here are heading northwards, but not quite to the extent, with the possible exception here of the dragonflies, not quite to the extent that you expect if they were keeping perfect track of climate. So evidence here that species are responding, but there are lags and they're not keeping up quite as quickly as we might expect. So that gets you thinking about why might there be lags and why might the empirical data not support perfect shifts in this situation. And gets you thinking very much about climate, but before going on about thinking about habitat rather, but before going on and thinking about the interactions between climate and habitat, I'd just like to talk a bit about some of the tropical work that I Ching went on to do. So traditionally, the idea was that temperature was not important in the tropical regions. So if you read papers by Rob Colwell and others, he cites Wallace and goes right back to Victorian times, saying that once Wallace was wandering around Wallachia, talking about benign tropical climates and species not being limited by climate there, the general feeling seemed to be that perhaps biotic interactions were far more important in tropical regions, and it was just in temperate high latitude regions that we had to be worried about climate. But then people started to challenge this idea, and I Ching came up with one of the first data sets to show that actually climate is important, and if you look at tropical species, they are shifting uphill. So this is I Ching here talking with Henry Barlow, and this is Mount Kinabalu on Borneo. So this was a fantastic data set that Henry Barlow had collected when he was an undergraduate student in 1965. And so what I Ching could do during her PhD was go back and resample the sites that Henry had done for his PhD. So these are the moths that Henry sampled, and that I Ching went back to the same sites and used the same techniques and sampled in exactly the same locations. So what she was able to do was work at this site and find out what changes had been over a 42-year period. So Mount Kinabalu, so here we are here in Southeast Asia. So Mount Kinabalu is the highest peak in Southeast Asia, going up to about 14,000 feet. So Henry was there with two others, Jeremy Holloway and a colleague. So this was an undergraduate project. The three of them just sort of headed off in the 1960s. And as a sort of member of staff now supervising undergraduate projects, makes me wonder a little bit about health and safety and wonder how much supervision they actually got. But anyway, they did a fantastic piece of work. They also recorded everything they did, took fantastic photographs. They published their work. And fortunately for them, the park was just being set up as a World Heritage Site in 1962, and they were establishing the route up. So this is park headquarters where the walk up begins, and the walk up and the locations that they sample now are exactly on the tourist route that everybody walking up Mount Kinabalu walks. So it was very easy to go back to the exact same sites. And as I say, with Henry, use exactly the same techniques and sample them exactly. So you can see here, these are some of Jeremy Holloway's photographs in 1965, and these are I Ching's taken from the same spot. And the good thing about Mount Kinabalu, because it is a World Heritage Site, all of these locations fall within the protected area. So there has been no land use change during that time. So there's been no logging, very little poaching. So arguably most of the changes come about through climate. So I Ching very bravely set off and resampled all of these sites, walking up and down this transect repeatedly. And after 2 years of sampling, analysis, and ID of all her moths, it all sort of boils down to this here, which is that for 102 of her geometric moth species that were also sampled by Jeremy Holloway, the distributions have shifted uphill by about 67 metres. Slightly less than you would expect, but nonetheless clear evidence that tropical species are responding to climate and shifting uphill as we would expect. But now we come on to this issue that we've already been talking about, that Georgina raised, this problem of land use change and loss of natural habitats. So this is what British species are having to deal with if they are dependent on forest habitat, surrounded by agricultural areas, and how do they get from one location to another. And if we're in Borneo, well, this is the sort of landscape that species are having to deal with, heavily fragmented. So this is an oil palm plantation. They don't plant on the steep slopes here, so this is some natural forest remaining. So any forest-dependent species got to try and jump across some of these agricultural areas if it's wishing to maintain its distribution and potentially move through and respond to climate. So these are the sorts of habitats that species are having to deal with when they're responding to climate change. So when we start to think about what sort of conservation measures we might want to bring in to help species respond and maybe deal with some of these lags, well, immediately the sorts of things people start talking about are the roles of habitat corridors and stepping stones, and they start talking about habitat connectivity and the degree to which we can help species shift through these fragmented landscapes by making them a little bit more connected. So I'll just show you a couple of examples for some work that have been done there. I'll then show you one slide to show how people have also been thinking about conservation for habitat heterogeneity to try and improve stability. I'm going to say something very briefly about translocations, but only to sort of raise it in your mind in case you want to discuss it later. I'm not really going to say very much about it, but just it's something that people talk about when they talk about response to climate change, and then I'm going to finish talking about protected areas. So thinking about habitat corridors and how we might want to alter our landscapes to help species shift through them, this is some work that Jenny Hodgson was doing with us and with colleagues in SCIY and with Natural England, focusing on a very heavily fragmented area in Yorkshire. So this is Yorkshire for 4 different natural habitat types, for woodland, heathland, grassland, and Myers fens and bogs. And as you hopefully can see here, incredibly fragmented county in terms of the natural habitat, and yet species are going to have to be moving through these landscapes if they want to respond to climate change. So the question here was that if we were to run this model and pretend to create more habitat, would it actually help species shift and help in range expansion rates? So the way we did this was to set up these stakeholder workshops and ask people where they thought new areas could be created and to get opinion. But we also imagined our own habitat recreation strategies, not just asking people where they thought it would be good, adding them at random or evenly, or trying to join up to make things the most connected. And as you can see here, these are the numbers for how fragmented these natural habitats are and the degree to which Natural England is committed to try and improve the amount of habitat that's there. And then what Jenny Hodgson did was she simulated how species would move through these landscapes once you'd added new habitats. And then we compared these strategies to essentially what would happen if you didn't do anything at all. So this is the location where she seeded around the edge of this area and then allowed species to move through and recorded how quickly it took to move from one edge to another. And just here I've given you some sort of indication of the types of ways in which she added habitat to the location, either randomly, as you can see here with these white dots, or to increase connectivity, which is this red blob here, or she had this link idea where you were going to link large areas or larger areas of habitat more specifically. And we had a few rules about where you could put habitat. You couldn't just put it anywhere. So what did she find then? So these are for the 4 different habitat types, and along the bottom here are the different ways of adding new habitat. And for all of these plots, what Jenny has done here is she's basically plotted them relative to doing nothing. So if you didn't add any habitat, what would you get? So as you can see here, most of them don't really work very well at all, adding new habitat, except here for the link one. And that seems to work also for wetland and for grassland and for woodland as well. But of course, some of these ways of adding new habitat differ, because if you can remember on the plot, the distribution of woodland is quite different to the distribution of heathland. So perhaps not surprisingly, the way you add new habitat does affect whether or not it's going to be successful or not. So more or less, the link strategy seems to be a good one. This idea of aggregating your habitat doesn't seem to do anything very well and doesn't do much better than doing nothing at all. But generally speaking, the more habitat you add, the better it is, and actually it seems to be relatively insensitive to species dispersibility. And even when you added lots and lots of habitat, some species never did expand. And one of the issues with this is that actually sometimes the link strategy just helped species already expanding to expand a bit better, and some species always failed. And one of the things that came out of this was to get us thinking that actually maybe the best spatial pattern for habitat for expansion may actually be different for persistence. But of course, if your species doesn't persist, then it won't be able to expand. And then this is some work that Tom Oliver was doing, who's in the audience. So this is analysis of the UK BMX transect data. So this is for butterflies, looking to see how habitat heterogeneity at sites affects population stability. So what Tom did here was to take a whole load of British butterflies at their transect sites, look at the way in which the abundance has changed over time. These transects were set up in the mid-70s, and then see how that is related to the local habitat heterogeneity at the site. And he quantified 3 types of heterogeneity. One is the diversity of habitats, then the aspect, so north, south, east or west facing, and then the degree of the slope. And what we have here are frequency plots for the different species in each of these bins. And in this case, what's being plotted here is the slope of the relationship between the variability in abundance and the measure of diversity here. So the significant and negative relationship here shows that there is increased stability with higher diversity. And that relationship is significant across the species for habitat diversity and for aspect, and a trend here for slope. So in terms of thinking about conservation and managing your locations and improving heterogeneity, then more heterogeneous landscapes will hopefully promote stability and therefore may buffer species against climate change. So I just want to briefly mention species translocations, but talking to Chris over lunch might be a better way of finding out a lot more about various views about what's going on. All I'm going to say is that people translocate species a lot. They do lots of reintroductions, especially for butterflies. This, you get into terminology here. What we're talking about here is moving species to locations where they've never been before. And the effort involved in trying to get permission to do this experiment was huge, because people feel very, very uncomfortable about moving species to locations where they've never been recorded. And that perhaps we can discuss that, but I'm not sure I'd want to do this experiment again. But anyway, we took this lovely butterfly, marbled white from Yorkshire, we took it up to County Durham, and we put it into a quarry where it had never been before. Our models, our climate distribution models, implied that the climate was very suitable for here, but it had never been recorded. And essentially what we did was, this is work with Stephen Willis at Durham. Essentially we introduced several hundred, the population increased, and as you can see, populations here increasing. The slope is very similar to locations where it's naturally been introduced. So it's where it's been naturally colonised. So growth rates were very similar. It seems to work. So you can do it if you wish, and I guess it becomes a political issue then. Is it something you really want to do? Okay, so now I just want to finish by talking more specifically about protected areas. And this is thinking about protected areas in relation to range shifting. And this notion that has started to sort of creep into the literature that protected areas might be in the wrong place, and concerns that because protected areas are static and yet species distributions are dynamic, that there's going to be some sort of conflict here, and maybe species are going to move out of protected areas for which they were set up in the first place, and maybe they won't arrive in the new ones. And what I'm going to do is talk about some work that a group of us, quite a lot of us actually, who members of the audience were involved with, looking at protected areas in the UK. And then I'm going to talk briefly about some work that Sarah Scriven has been doing, a PhD student, which she started looking at the role of protected areas to conserve species on Borneo. So 2 examples to sort of highlight the issues of protected areas and how well they may work for conserving biodiversity. So say, first of all, looking at UK protected areas, so there's a large group of authors looking at this very much in relation to range expansion. So this is the protected area network in the UK. So these are the locations of the SSSIs. And we did 2 types of analysis, of which the Dartford warbler here and the silver-spotted skipper are 2 examples. So we had 7 species with a lot of information that had been very well studied. And what we have here are core sites in blue and the colonised sites in red. And what we wanted to know was, do they end up in protected areas when they're colonised more than you would expect by chance? And that is the case. So after a huge amount of work and analysis by Pippa Gillingham, what we found was that colonisations do occur disproportionately within protected areas. So certainly during range expansion, protected areas are being used by species and they are colonizing them more than you would expect for the availability of protected areas within the landscape. So we did this for species for which there are excellent records, and Pippa also did it for an additional 250 plus invertebrate species. These data are a little bit messy, they're confounded a little bit more by recording effort, but essentially the story is the same. If you get a value on this x-axis here of more than 1, it means the species is more likely to colonize a protected area than you would expect from the availability of protected areas in the landscape. And again, these are frequency plots, the number of species in these bins for the degree to which it is more likely than you would expect by chance. So 3 times more likely, 30 times more likely, and so forth. And this was an analysis that Pippa did on behalf of the referees who thought that urban areas and so forth should be excluded. So finally, thinking about this work about tropical protected areas and are they in the right place? So this is some work on Borneo. This is the elevation of Borneo and the current land cover. About half of Borneo is now still covered by tropical rainforest. And this is the protected area network on Borneo. So more protected areas currently on Borneo than there are in the UK. But if you look at these 2 maps here, you've got a lot of low elevation areas. So this is the Dipterocarp rainforest, high in biodiversity, important for timber. Dipterocarps are taken for timber, and when they're removed, this is where all the oil palm is being planted. And as you can see here, a lot of these protected areas are at low elevation. So as you can see here, 65% of the land area of Borneo lies below 200 metres, but less than 10% of that area is protected. And as you move up to higher elevation, where there's less land there, but actually huge areas of this are very high proportion of it is protected, which arguably is quite good if that's where species are going to move as they shift uphill. So what Sarah's been looking at is she's been taking a protected area focus, and she's been arguing that if species are going to leave protected areas and try and get to new protected areas, under a climate change scenario such as the A2 SRES climate change scenario, you're going to have to get to somewhere that is on average 3 degrees cooler than where you are currently. So you might be all right and be somewhere quite topographically diverse, and you can just move uphill and stay put. But for a lot of other places, they're in protected areas which are very flat, they're very homogeneous, they don't have cooler areas in them, and they're going to have to shift to new protected areas. And what she's found is that many of these low-lying protected areas are too isolated for these species to leave and get to new protected areas. And this just gives you an idea of the sorts of output that she gets. This is just example output for a species which has about a 2-kilometre ability to disperse per generation. And what's shown here are refugia sites where you don't have to move. So here we are, this is Mount Kinabalu Park here, lots of places to move up to. You don't need to move in any of these blue areas. The yellow areas are where you can successfully get out and get to a blue area, and then anything that's red, you can't get out of it. Moving through areas that are not protected, but you just can't get to a protected area. So there's problems here that a lot of these areas are just too isolated for species to leave them under projected climate change and get to a refuge. And especially in the state of Sabah, and this is all oil palm here, and these are important protected areas for proboscis monkeys and Sumatran rhinos, and they're sort of stuck in those protected areas and can't get out. So just to finish off with a good example of how this work is being perhaps a bit of a good news story, I guess. So in the state of Sabah, there is a large area of state-controlled forest which contains these protected areas shown here, which are these locations here and here. And what the state government has decided to do, being worried about the ability of species to move between protected areas, what they've done is they've increased the area that's protected, so that's the green area, beyond the boundaries of the legally protected areas to include more areas, and they're also going to include these brown areas as well into full Class 1 protection. So this is all owned by the state, it's all production forest, except for these areas that are protected, and these blue areas which are oil palm. So because it's all been controlled by the state, if you like, they've been able to make this decision, and these brown areas are going to turn blue quite soon. These brown areas are going to turn green quite soon. And as you can see here, there's quite important corridors, and they're linking it together. So I sort of think maybe they've been listening to John, and it's sort of a bit of a more bigger, better connected. There's certainly a lot more of it, certainly a lot of a bigger area, arguably perhaps not better because there's not any plans to do any sort of management, but it is connected. So perhaps a good news story, but I won't tell you the reason why they're doing it because that's not quite such a good news story. We can come back if you want to know. Anyway, so conclusions then. So species are shifting, going uphill and polewards, and of course in the tropics there's this concern about biotic attrition because there's not a pool of species that are warm adapted to replace these ones at the equator. So maybe translocations. Habitat recreation to increase connectivity, but is it actually going to help those species we want, or maybe it'll just help the ones that are already doing okay? Yes, in the UK, protected areas do seem to be in the right place for helping species shift, but maybe if you move somewhere at lower elevation and look at where species are leaving, then you find that many protected areas are very isolated. And then, of course, what you shouldn't be forgetting is carrying on a lot of the conservation management in existing areas to make sure that local population is boosted, because obviously you're not going to get any propagules and any range expansion unless you've got a healthy population. So thank you to all these people. I sort of sound a bit like Margaret Thatcher and the we, you know, we've done this. Well, actually, I haven't done any of this. I just talk about it. It's all done by all of these people here, so thank you very much.